on to I should say, part 2 of our series on sealing technologies. Today, we're going to talk about the most common way of sealing processed liquid, and that is mechanical seals. Mechanical seals are a highly talked about and highly debated topic because when a pump fails, mechanical seals are typically why it fails. So let's talk about how mechanical seals work and how we can extend the life of them. A mechanical seal has two sealing areas, what we'll call a primary sealing area and a secondary sealing area. The primary sealing area consists of a primary ring and a mating ring. That's where most of the wear takes place and the most common failure mode. Secondary sealing areas would be O-rings, wedges, gaskets, things of that nature. The combination of those two will seal liquid from the atmosphere. The common question is, do mechanical seals leak? Well, yes, they do. Most of the time, you won't see the leakage, or you might see a drop a day or something like that. The reason for that is the processed liquid comes across the seal faces, and as it does, it hits the atmosphere and most of the time will evaporate. So you don't see it. So if you're pumping a very hazardous or dangerous liquid, that might not be good enough, and most times is not. And so we have to take some extra precautions and look at other types of sealing technologies, which we'll talk about later, to help the environment. Okay, there are two basic options for mechanical seals, and one is a pusher seal and one is a non-pusher seal. Simply stated, a pusher seal is a seal that is going to have static movement of the secondary sealing surface. So if that's an O-ring or a Teflon wedge, the movement on that seal takes place to make sure that the seal face is tracked together properly and have the proper loading. The other type is a non-pusher seal, which has a static O-ring, and all the movement takes place in front of that, or most common version of that would be a bellows type seal. Generally, non-pusher seals are more expensive than pusher seals, but they both have very distinct service opportunities in the industry. In order to correctly pick a mechanical seal for a service, we would need certain information from the end user, and that would be the most common thing. Would be what are you pumping? That's where we start, and then from there we would want to know what the temperature of that liquid is, what the vapor pressure, viscosity, and operating pressure. And operating pressure, both suction pressure and discharge pressure. Most cases, suction pressure is going to be very low, but seals are sized based on all those operating conditions. Material options are various. The basic arrangement would be a carbon face versus a hard face like tungsten carbide or silicon carbide. The metallurgy, most common metallurgy, of course, would be 316 stainless steel. O-ring material can be anything from Buna to Viton to Aflas to Calres and everything in between. Selection of mechanical seals and the sizing of mechanical seals are based on several factors. The most obvious factor would be the shaft size or the shaft sleeve diameter. That's where we start. Next thing we want to know is what the stuffing box looks like. How much room do we have in there to fit a mechanical seal? The other thing we need to know is what is the distance to our first obstruction, which means in a pump, the seal area or stuffing box area has a certain clearance between it and the bearing frame. And so we need to understand what that clearance is and how much room we have to work with, and we go from there. Now, I can tell you that most ANSI pumps in the market are designed to fit the standard cartridge seals in the industry. So those pumps no problem. You can get just about any seal type to fit in that pump. Other pumps, other specialty pumps, need to be looked at a little bit more closely. There are two different types of mechanical seals. The first one is a component seal, which consists of all the major components you need that are within the mechanical seal. And that would be the rotating element, the mating ring, which is generally static and pressed into a gland, and of course the gland. Those three parts make up a component seal. The second type, and probably today the more common version of that, is a cartridge seal. Just by looking at it, you can see that that's a fully assembled unit, and we'll talk about some of the advantages and disadvantages of each type of seal. In this segment, we're going to talk about the differences, advantages, and disadvantages of component versus cartridge seals. As you can see, we have three components that make up the primary part of a mechanical seal. The faces on these seals are lapped to millions of light bands, which you cannot see with the naked eye. The picture probably shows how shiny they are versus the backside of the seal, which is kind of dull as in comparison. The seal faces are designed not to touch. Anything you get on them, if you're working on a bench and you have dirty hands, dirty bench, debris around, anything of that nature that can get onto the seal faces could result in a seal failure pretty immediately. So the first thing is you want to handle the seal with kid gloves. The next thing to keep in mind is on a component seal, there's certain dimensions that have to be attained in order to get the proper face loading. If those dimensions are not maintained, and for instance, the face loading is too heavy, then you're going to get wear on the on one or both of the faces pretty quickly, generate an awful lot of heat, and eventually have a seal failure. If the loading is too loose, then you could have a seal failure as soon as you start the pump up. So each component seal has a drawing associated with it, and that drawing shows a operating length, and that operating length has to be maintained. Now, when you look at a component seal, you take a pump apart, you cannot determine how the face loading is going to occur unless you go through a series of events. First thing you have to do is put the gland in place without the seal. And that would be what we call a reference point. You mark that, ascribe a line, then take it apart. Now you want to go ahead and install the rotary portion of the component seal, and the back of the seal is going to sit on that operating length dimension. So as you can see, these dimensions could be in 1/16 of an inch, 32nds of an inch, require very fine tuning, and if you're off a little bit or your ruler is not working that day, any variation of that could cause you to have a seal failure. So there's your component seal. Now we have our cartridge seal. As you can see, the cartridge seal is fully assembled. Doesn't require any dimensional checks prior to installation. Basically, all you do is lubricate the O-ring, install it on the shaft, lock your gland down. There are clips on the OD of this collar. The last step would be tightening down on the retaining screws and then releasing the clips. And when you release the clips, now the seal is set at whatever that factory tolerance is for face loading. It's a very easy installation, Maintenance guys love to work on them because it takes a whole lot less time. The other advantages to a cartridge seal is that they all are associated with repair programs. So if you say, well, okay, what's the disadvantage of a cartridge seal? Well, it's going to cost more. And the savings comes in because you have really no error with installation. Everything's contained, so you're not touching any seal faces. And when the seal has gone through its useful life, it's still worth something. Mostly all seal manufacturers have repair programs which are associated with cartridge seals, and generally it's half the price of new. So the seal retains its value, and you never have to pay full price unless the gland is totally damaged or cut in half. Geiger offers a 1-hour training seminar, which is a seminar which goes through the entire pump teardown, seal installation, and reassembly. And it's available on our website.